Hello friends, and welcome to another lecture on chemical engineering thermodynamics. Today we will be studying a problem that has come in Mumbai University Chemical Engineering Thermodynamics 1 question paper. This problem has come on December 17th and it is worth 20 marks. The problem is on your screen. 1 kilomole of oxygen having an average CP value of 32.22 kilojoule per kg Kelvin undergoes the following changes successively. Find Q, W, delta U and delta H for each step and for entire process. The process is reversible and ideal gas behavior is assumed. Well, the processes that it undergoes is given in 1, 2, 3 and 4. Well, at the outset, I would like to clarify to all my viewers that the value of Cp given here is 32.22 kilojoule per kg Kelvin, and that has come in the question paper. All the researchers say that the value of oxygen in molar units is 32.22 kilojoules per kmol Kelvin. Therefore, we have to take this value for oxygen. The value of Cp for oxygen should be read as 32.22 kilojoule per kmol Kelvin. That should be read as the value for R. So, having clarified that, how do we solve such problems? First is that all the steps given, that is from steps 1 to 5 given, should be traced out on the pressure volume diagram. And a slight modification here. The volume here will be in meter cube per kmol. Yes. Now let us take and trace the processes. The process number 1 is it is expanded isothermally from 800 Kelvin 2.5 megapascal to 0.5 megapascals. So this is 2.5 megapascals and this blue is the isotherm which is at 800 Kelvin and it goes from 0.1 that is 2.5 megapascal to 0.2 that is 0.5 megapascals. So this is 0.5 megapascals. Now from 0.5 megapascals, it goes to a lower pressure of which is not known, but it goes to an isotherm of 400 Kelvin. Therefore, the pressure at 3 is not known. We should calculate it out. Now from 3 to 4, it goes isobarically and it goes to an isotherm of 300 Kelvin. As it is given here, it is cooled at constant pressure and it goes to an isotherm of 300 Kelvin or it goes to 300 Kelvin. And from point 4, which is at 300 Kelvin, it is adiabatically compressed to 2.5 megapascals. And we do not know the value of this isotherm. So I would put as a question mark. And from here, it is again heated back to 800 Kelvin. To solve this problem, we should know the temperatures at each and every state. That is state number 1, 2, 3, 4 and 5. What we do not know here is the temperature at state 5. And we do not know the pressure at state 3. So let's get about calculating that first. So for that, I should just remove this out. Let's start the calculations. Yes. First, we need to calculate P3. Now, we know that from ideal gas law, P3 upon T3 is equal to P2 upon T2. Now P3 is unknown, T3 is 400 Kelvin, and P2 is 0.5 megapascals, and T2 is 800 Kelvin. Therefore, we get P3 as 0.25 megapascals. So we should make a note of it. This is 0.25 megapascals. Now from 4 to 5 is an adiabatic process. So we can find out T5. We need to find out T5 here. T4 is known, it's 300 Kelvin, and T5 needs to be calculated out. So we know that from adiabatic law, T5 by T4 is equal to P5 by P4, the whole raised to gamma minus 1 over gamma. Now, for our reference, we will calculate the values of the constants that we require so that we can use them quickly. So Cp is 32.22 kilojoules per kmol Kelvin, and Cv will be equal to 32.22 minus 8.314, and that makes it 23.906. So Cv is 23.906 kilojoules per kmol Kelvin. Cp minus Cv is equal to R. This is what I have used. Now gamma, which is nothing but Cp over Cv, so let's calculate the value of gamma. So the value of gamma is going to be 32.22, and this is 23.906. So divided by 23.906, and that is 1.3477. So we can take it as 1.348. So gamma is 1.348. Therefore, T5 over T4, which is 300 Kelvin, is going to be equal to P5, which is nothing but 2.5 megapascals, 2.5 megapascals, and P4 is 0.25 megapascals, the whole raised to 1.348 minus 1 divided by 1.348. Now let's calculate this value. So now we have this as 2.5 divided by 25. So let's take this. Let's start the calculations. 2.5 divided by 0.25, 10 raised to 1.348 minus 1 divided by 1.348. This is equal to 1.812. So we have this as 1.812. Therefore, T5 is equal to 1.812 multiplied by 300, and that is equal to 543.8 6. 543.6 kelvins. Now let's make a note of that in the diagram. So this temperature is 543.6. Now to solve this problem, we have to calculate the delta U and delta H at each and every step. So let's make a table for it. So this is the table I draw for it. Now the first column is the process, the next column is delta U, the third column is delta H, the fourth column is Q, and the fifth column is W. So I noted down process, delta U, delta H, Q, and W. All the units will be in kilojoules. That is because the basis is 1 kilomole. Basis of calculation is 1 kilomole. We are taking 1 kilomole of oxygen gas. So let's start our calculations now. So the first thing that we need to calculate is for process 1, 2. So process number 1, 2 is an isothermal process. Therefore, delta U for this is 0, delta H for this is 0. Now Q and W. The formula for W is equal to nRT ln of P2 by P1. This is equal to 1 kilomole into 8.314 into T is 800 into ln of P2 was 0.5 by P1 was 2.5. Now the value for this is 1 into 8.314 into 800 into ln of 0.5 divided by 2.5. This is equal to minus 10,704.69. Now we shall be rounding off the decimals because the figures are quite high and the decimals can be rounded off in favor of the higher decimals. So the rule is that if we have 0.6 and above, we should round it off to 1. So I should take this as minus 10,705. So I will take this as minus 10,705 kilojoules. Now, applying the first law for an isothermal process, we get U21, that is not 21, that would be 1, 2. That is from 1 to 2 is going to be equal to Q plus W. Now, the internal energy change for the isothermal process is 0. Therefore, Q is equal to minus W, and we get the work as the heat as plus 10,705. Now, process 2-3 is a constant volume process. Now, for this constant volume process, T2 is equal to 800 Kelvin and T3 is equal to 400 Kelvin. Now delta U 3 will be equal to 1 kilomole, which is the basis, into CV, which is 23.609 906 906 906 into 300, that is the final temperature, minus the initial temperature, that is 400. Now this will be equal to 1 into 23.906 into 400 minus 800. I just made a slip of the tongue. Minus 9642.4. So this is not 300. This is, let's correct it. The final temperature is 400 and the initial temperature is 800. And I have accordingly done the calculations, 9562.4. So we take it as minus 9262. We round up the decimals. So 9562. So yes, minus 9562. So now we divide it by 23.906 and multiply it by 32.22, and we get the value as minus 12,888. Minus 12,888. Now I have done a simplification here, which I will explain here. Delta H23 for any process for an ideal gas is going to be N into Cp into T final minus T initial, which can be written as delta U23, which is nothing but N into Cv into T final minus T initial divided by Cv multiplied by Cp. And this should ease out a lot of calculations. So now we calculate delta H accordingly and we get the answer as minus 12,888. So now this process was a constant volume process. So the work is going to be equal to 0 and the heat is going to be equal to delta U. So we note it down, minus 9562. Now we go to process 3 to 4. Now process 3 to 4 is a constant pressure process. Now we have here T3 comma T4. Now what is T4? T4 is 300 Kelvin. Therefore, I have now explained how to calculate delta U. Now I will be directly doing the calculations without writing down the formulas. So delta U is going to be 1 into 23.906 into 300 minus 400. That is equal to minus 2,391 minus 2,391. We divide this by 23.906 and multiply it by 32.22 and we get 3,222 minus 3,222. Now since this is a constant pressure process, the Q will be equal to minus 3,222. And if we apply the first law, we are going to get delta U 3, 4 is equal to Q plus W, which is equal to as minus 2,391 is equal to minus 3,222, because Q is equal to delta H for this process plus W. So therefore we have 3,222 minus 2391. That's 831. That's 831. Now we have T4 as 300 Kelvin and we have T5 as, let's make a note of it, 543.6 543.6 kelvins. And this is an adiabatic process, so Q will be equal to 0. Let's calculate delta U, which is going to be 1 into 23.906 into the final temperature, which is 543.6 minus the initial temperature, which is 300. So that's 5,823. So that's 5,823. So we divide this by 23.906 and we multiply it by 32.22. This is equal to 7,849. 7,849. Since Q is equal to 0, therefore naturally work is equal to 5,823. Since we apply the first law, delta U is equal to Q plus W. Q is 0 and work is equal to 5,823. Now let's go to the final process, and the final process is we have T1 is equal to 800 Kelvin. Now this is a constant pressure process, so let's do the calculations. 1 into 23.906 into the final temperature, which is 800, minus the initial temperature, which is 5,000, not 5,000, 500, 543.6. That's 6,129. 6,029. Divide this by 23.906 and multiply it by 32.22. We get it as 8,261. 8,261. This is delta H. We have done the calculation as done before. Since it's a constant pressure process, the heat is equal to 8,261 and the work naturally is going to be the difference in the internal energy minus the enthalpy. So let's calculate it out. 6,129 minus 8,261. Now this is equal to minus 2,132. So that's minus 2,132. Now for a cyclic process, we should always check that the addition of all delta U and all delta H is equal to 0. That is the check. Because for a cyclic process, the change in internal energy and the change in enthalpy is equal to 0. So let's do that. Minus 9,562 minus 2,391 plus 5,823 plus 6,129, and we get this as minus 1. Now this error is expected because we have rounded off the decimals, and we should take this as 0 because this is going to be an insignificant error. So we take this as 0. Now let us add up delta H, which is minus 12,888 minus 3,222 plus 7,849 plus 8,261. That's a 0. All the decimals perfectly taken into account. Now let's add Q and see what do we get. So that's 10,705 minus 9,562 minus 3,222 plus 8,261. That is 6,182. 6,182. Now let's add up all the work. That's minus 10,705 plus 831 plus 5,823 minus 2,132, and we get it as minus 6,183. Now we need to understand here, we get a difference in 1 in some cases because we have rounded off the decimals as per the rule that if the decimal is zero point 0.5 or less, we take the lesser value, and if it is greater than 0.5, we take the higher value in the units place. So this is but natural, you will always get a difference of 1. Well, this is an insignificant difference as compared to the results that we have. So we should take this as 6,182. We can neglect the 1, and there we get summation Q is equal to minus summation W, which is true for a cyclic process. So that was all, guys. And this is the last problem on cyclic process that I will be taking because I have actually demonstrated enough problems on a cyclic process. If you have any comments, do write it down. Do like and subscribe my channel. That is very important. It keeps me motivated to make more such videos for you. Like, subscribe, write comments. Write comments. This is very important. Ask questions. This is very important. Okay? It gives the author a feedback that his work is being viewed, his work is being audited, and therefore he gets some focus on what he needs to do next for the students who are watching his videos. Goodbye, friends, and take care.